Okay, so this is going to be a very informal presentation on elementary geometry, really elementary school stuff. So you might wonder if it's so elementary, so basic, why bother with it? Well, as you'll see, it's not about the geometry itself, it's really about the reasoning, and reasoning is generally applied in all of mathematics. The point of using geometry is that it's quite visual. And this particular type of geometry is very easy to do. So, and also I'm being quite informal with this, so a lot of time I'll be going, you can see, and I'll point to something. So that really helps. But the point is that I really want to show how the mathematical reasoning works. I don't know if I'm being quite effective about it. That remains to be seen. And the way I want to do this is that I'll start with as few assumptions as possible. And from there, we'll get a bunch of other stuff, provided we are being logical with our steps. And I'll also try to motivate those assumptions as well. So I really want you to think that you are taking as little as possible as given. And if you are logical about it, you can get a whole lot of stuff from that. So I'll write down the assumptions first. So the assumptions are as follows. So the first assumption, I don't really think it's an assumption. I mean, it is an assumption in a formal sense, but I mean, there could be some implicit assumptions along the way as well, but I'll only be using these two, starting from these two assumptions explicitly. I mean, one could say that I'm assuming the existence of algebra, but we're not being that pedantic about this. So, the first assumption is that the angle subtended by a straight line is 180 degrees. I think there's nothing new about that, everybody knows that. But the only thing you might have a concern with is this 180. It seems rather arbitrary. And this really comes from the fact that a full rotation is 360 degrees. So you might ask, why does rotation have 360 degrees in it? Well, this is purely historical. This 360 degrees, and I mean, I looked up into it by Wikipedia, to be honest, but the only thing that I found was, and I'm not sure if this is quite accurate, is that in the olden days, when people used to think that the Earth was at the center and the Sun and all the other heavenly bodies went around it in perfect circles, so at that time people used to think that there were about 360 days in a year instead of around 365. So if you have perfect circles for orbits, and if you have 360 degrees in a circle, 360 days in a year, so the Sun will move by exactly 1 degree per day. So that's quite nice, but we know this stuff isn't correct. But the 360, we're stuck with that. So we'll just work with it. But it really doesn't matter, if I'm honest, it really doesn't matter if I choose to call this 100. You could call this A, B, C, 200, 100, whatever you like. It really doesn't matter. Because mathematics doesn't care what us humans choose to call the quantities in it. I mean, they're just there. So, as you'll see, you can do this with anything. The point is that I'm just assigning a value to it because we're familiar with this value and it will make things quite easy. The second assumption, and this is going to be quite a proposition, is that if I have two parallel lines and I cut them, so this angle and this angle are the same. I think this is called corresponding angles. And I'll try to, give a bit of physical reasoning for this, but if I'm honest, it's going to be a circular argument, but let's see if this helps. So, if we have straight line like this, and I cut the line like this, right? So of course this gives me an angle, right? Now what I want to do is, I just want to take this line, I'll make a copy of this, and I'll just drag it down, right? So I'll just take this line and drag it down. So I'll just drag it here. Now, I have no other point of reference for these two lines except for this line. Right. So you can see that if these two lines are to be parallel, then the relative inclination between these lines and the relative inclination between these lines must be the same. For example, if it's not the same, if the relative inclination is tilted, if I increase the relative inclination of this line, so if it's like this, so you can see at some point this line will cut this line. So this one will parallel. Similarly, if I decrease the relative inclination, so if I make this line like this, so this will meet this line at this point. But if the relative inclination is exactly the same between these lines and these lines, then these two lines will be parallel. You can see that. And of course, relative inclination is just another word for angle. So what I'm really saying is that if you want to have these two lines parallel, then these angles must be the same. Right? Okay, so we have our two assumptions right here. So even if you're not convinced about the angle property, just take these as given. So I'm really asking you to take these as given, but this will give us loads of further stuff, as you will see right now. So, if I cross two lines, that gives me, let's say, this angle. Let's call it A. But from this, we know that the total angle on a straight line must be 180. So if this is B, then A plus B must be equal to 180. Right? So, in other words, B is equal to 180 minus A. So I'll just write it down. So, this is 180 minus A. Now, take this straight line. By the same reasoning, this angle should also be equal to 180 minus A. Right? Now take this line. If this is 180 minus A, then the only angle that can make the whole sum equal to 180 is that if this angle is A. Right? Because A plus 180 minus A gives me 180. But let me just get rid of a few angles and let's see what we have done here. So what we have really gotten is this. These are called vertically opposite angles. So this is a nice property we have. So if this is B, then this is also B. Right? By the same reason, if this is B, this is also B. This is pretty trivial stuff. But just keep this in mind and let's see what this gives us yet again. I'm going to play the same game, but now let's keep this angle right over here. So if this is A, this is also A. Let's forget about this for a moment. Let's play the game. So if this is B, then this is also B, and this is also A. Right? We just did this. Now, I'm going to get rid of some useless angles. We have this property. These are called alternate angles. But if you cut a straight line, if you cut two parallel lines by a straight line, these opposite angles, and by the same reason, these angles are the same. And this is quite a powerful property, as I'll now show you. But look, we started with 2, we've gotten 2 already. So we have gotten these vertically opposite angles. And we have gotten these alternate angles. Now this is quite a useful property. Look, if I have a triangle, and triangle, 3 angles of course, A, B, C. Now if I just extend the base like this, and I draw a line passing through this point as parallel to the base, so like this. So by the alternate angle property, if this is C, this is also C. If this is B, this is also B. So the triangle has angles A, B, C, right? But look, this is a straight line. We see that the sum A, B, C of the angles of a triangle is equal to the angle subtended by a straight line. So if the angle subtended by a straight line is 180 degrees, then the sum of the angles of a triangle is 180 degrees. Sum of angles of a triangle is equal to 180 degrees. But let's forget about 180 degrees. Let me just repeat what I said before. That the sum of the angles of a triangle is equal to the angle subtended by a straight line. Notice that I don't have to say what is the value of the angle subtended by a straight line. This is the intrinsic relation, that the sum of the angles of a triangle is equal to the angle subtended by a straight line. So if the angle subtended by a straight line is 180, in radians it's pi, so the sum of the angles of a triangle is equal to pi in that sense. So it could be any value, but you see, if you're consistent, the answer will come out the same. You don't have to give this any value. This is what matters, and we're not talking about any specific value here. So these two have given us the sum of the angles of a triangle is equal to 180 degrees as well. So we started with 2, we've already gotten one more. So what about a square? I mean this is more of a rectangle, but rectangle or square, it doesn't matter. What is the sum of the angles for four-sided figure? I don't know for the moment. But what I can do is take this four-sided figure and split it into two triangles. I know this gives me total angle sum of 180 degrees. This gives me 180 degrees. So the total must be 2 times 180 is equal to 360 degrees. I can do this with any square, or any rectangle, any four-sided figure in general. I mean, take this, I can make it like this, or this, 180, 180, 360. It will always be 360 because you can decompose any four-sided figure into two triangles. Let's try with five-sided figures. One, two, three, 1, 2, 3. 1, 2, 3. So 3 times 180. That gives me 540. So the sum of the internal angles of any five-sided figure is 540 degrees. Five-sided polygon, I should be more precise. We can go on, but you might be inclined to think that can any n-sided polygon be decomposed into triangles? Well, I can't draw all of the n-sided polygons because they are infinite, but I can sort of try to argue from a different line of reasoning. What if instead of asking the question that can I decompose any n-sided polygon into triangles, I can ask, can I make any n-sided polygon from triangles? That's a bit different. Let me show you. So if I start with one triangle, what do I do to make it into a four-sided figure? This is a three-sided figure. Well, I just add another triangle. What do I do to make this into a five-sided figure? I add another triangle. And so on. So you can see that instead of thinking in the way that can I break any n-sided polygon into triangles, I can make any n-sided polygon from triangles. And I mean, this is quite nice because you see, triangle has three sides, right? So what I'm really doing is I'm adding two sides and taking away one. I'm adding two sides and taking away one. And that amounts to adding a triangle, but what it really does is increase the number of sides by one in total. So by adding a triangle, I increase the number of sides by one. Alright? So now I can have the series. If I have three sides, I have 180. So if I add a triangle, I increase the sides by one, but I add 180 degrees to the total internal angle, so that's 2 times 180. If I add another triangle, I get 3 times 180. And so on. Notice the difference between 3 and 1 is 2, 4 and 2 is 2, 5 and 3 is 2. So these are the sides, this is the total angle, and this is the multiplier for the angle. And the multiplier for the angle is always 2 less than the number of sides. So if I have an n-sided polygon, so its total internal angle is given by n minus 2 times 180. And this 180 comes from the fact that any n-sided polygon is basically made from triangles. So that's that. So now we have the fact that the total internal angle of an n-sided polygon I started with these two and I got all of the polygons as well. So like that's getting infinite stuff. So this is in a nutshell basically what I wanted to show. I hope I managed to get the point across. This was really very basic elementary stuff. I tried my best to explain this. I'm quite new to this lecturing stuff, so I hope I'll get better as time goes on. But I really appreciate feedback as well. Thank you.